Yes. Live transcription enabled. Come on, enable. There we go. Good. Okay, so we enabled closed caption recordings started. So good evening, class. Welcome to Wednesday's class of week 3. So next week we start in the classroom. So MS 118, first floor of the Math and Science building. It's on the syllabus. Remember that Monday is a holiday. So that's President's Day. So don't come to class Monday. This Friday is also a holiday if you got any classes this Friday. Let's see. What else? Also, tomorrow we will have an office hour session from 6 to 6:50 right here in our remote online classroom. Okay, for the office hours next week, it'll be in conjunction with the with what's in the syllabus. So I might have to start in the LRC. It depends on what class is before us. Hopefully there's no class right before us. If that's, well, there won't be before us. So I'll be in the classroom before us because I got another class from 5 to 6:25. So between two classes, then I'll be in that classroom. But you can see I might be kind of busy putting stuff on the board and that's there, but I'll be able to field any questions that people might have. I'm trying to do office hours before that class also, probably about 4 to 5 o'clock before that class, hopefully, if there's nobody in the classroom. Otherwise, I'll have to do it in the LRC, which the library, which I've written on the syllabus. Anyway, we'll see. We'll have to play the office hours next week by ear. What's also happened is well, another thing, I adjusted the lighting. So I tried to eliminate any light hot spots on the board. The only one I got on the board right now, you can see over on this side of the board is from the chat strip. So when we get started with the board, with the review, I'm going to drop the chat strip. It'll still be up if you want to write something in the chat and I can take a look at it later on, but I want you to sign in the chat also. But that'll eliminate that hot spot on the board. So I've adjusted the lights on the outside, hopefully to give me better lighting on the board without the glares. Also, the transfer center has sent us an email right here, and I think you should be getting it also. I don't know why you don't get it. I'll try and put these sorts of things in. I'll either send them to you or put them in the Canvas. I'll have to figure out how to put them in the Canvas. But anyway, so the transfer center will be having spring 2022 transfer talks as we go along. So when I get information on those talks, I'll let everybody know about it. So they're getting people ready for the fall 2022 transfer applications and even looking forward to 2023 transfer applications also to the CSU and UC systems. So the California State Universities and University of California systems. And they have other colleges usually come on campus to give presentations also. And sometimes they'll have a whole week set aside, which they call transfer week, and they'll have all these colleges and universities come in, and they'll at least have representatives there. Typically, they set up in front of the cafeteria or inside the cafeteria. But when that happens, I'll let everybody know about it. Okay, so hopefully this lighting works out better for you. It took me a while during the previous class to actually set it up because I can't do it during the daytime. I have to wait till it gets dark before I can set it up. Okay, hang on real quick. I need to position. I'm about to run out of ink here. Need one black one. There's a black one. Okay, good. I suspect that I will be getting short on those two ink pens here during our presentation. So any questions, any administrative type questions, schedule, what's going on, anything like that? Let's see, any other notes on the schedule? Hang on, let me see. If we got any other notes on the schedule right here. Let's see. Well, we got the holiday next week. Let's see. This Friday is a holiday also. So test one, I'm not going to do next week as it says on the schedule. I'm going to do it the following week, but it'll cover everything in the first 3 weeks. So all those homework assignments and what we covered in the first 3 weeks. Okay, that's what will be on the test. And I might have to readjust the rest of the test schedule to spread everything out properly. I might even have to drop a test. So I'm thinking about that too. So we'd only have 3 regular tests and the final. Anyway, we got to go with the flow and try and make things work for the situation that's taken place. Spring break isn't way till the end of March, so don't worry about that. Okay, I'll let you know when that's coming up. And it's on the schedule also. Okay, so any other administrative questions, schedule, text, anything like that? Okay, I'm going to drop the chat, but it'll still be there. Please sign into the chat. Or if you have questions, you can put them in the chat too, and I'll get back to you. But I'm going to drop the chat so we won't have that glare on the board back there. Okay, then I'll start looking at the review here behind me. So we started off last time finishing up 8.5. So we actually worked one problem and set up another one. So we worked a problem on 3 variable words, 3 variable word problems, a word problem wherein you get 3 variables. So you have to come up with 3 equations. So we worked one on value mixture, and then we set up another one on interest, just so you could see what that would look like. We didn't work that one. And then we went right into 8.6. So in 8.6, we're talking about solving a system with matrices. So a matrix. So a matrix, the plural is matrices, is a rectangular array of numbers. So up in the top of the next column, I have the matrix parts. So the matrix is enclosed with 2 brackets, one on each end, and it's arranged by rows, which go horizontally, and columns, which go vertically. So the 2 rows are horizontal, 1 and 2. 1's on top, 2's below it. If there was another one, that would be 3. So it goes 1, 2, 3, top to bottom. The columns go 1, 2, 3, left to right. The individual items in the matrix, the individual numbers in the matrix are called elements. Those are the elements. Sometimes they're referred to as items, but typically we'll call them the elements of the matrix. It's enclosed with brackets. Okay. And we call it a 2 by 3, 2 by 3. So this is a 2 by 3 matrix. That means there are 2 rows, 3 columns. So we always call it rows by columns. 2 by 3, 3 by 3, 3 by 2, etc. System representation. So we can use this matrix to represent a system. So over here, I have the system. So the first equation, let me get my seat out of the way. There. The first equation is 2x plus 3y equals 5. The second equation is x minus y equals 4. And I have a line under it. So that's how I represent my 2 variable system. Then I can write from that system, I can make what's called the augmented matrix. So the augmented matrix for the first row, I have 2, 1, dash, 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 5, 2, 1, 5. In the second row, I have 1, negative 1, 4, 1, negative 1, 4. You only put in signs if it's negative. If it's positive, there's no sign. And to represent the equal sign, I have a column of dashes right there. So that's called the augmented matrix. So a couple of notes here at the bottom. 1, each matrix row is an equation. So notice each row in here is an equation. So the first column represent the x's, the second column the y's. So each column is the variable coefficients for x's, y's, and numbers. So this is the x column, the y's column, the equal sign, and the numbers right there. So my whole system is represented there. I've eliminated the variables. They're still in there, okay? Theoretically, I just don't see them. So that first row is the x's, the second row, the first column is the x's, the second column is the y's. Okay, so let's move on here. So over here, the solution representation. So the system notation to solution matrix. So over here, I have the system. The system for this, for that equation that I set up before on the previous board is x equals 3, y equals 1. So that actually translates into two xy equations. So the first one is 1x plus 0y is equal to 3. And the second one is 0x plus 1y is equal to 1. And then that translates into this matrix right here. Whoops, there we go. Into this matrix right here, 1, 0, 3, 0, 1, 1. There should be a 1 there. Make a bigger 1. There we go, 0, 1, 1. Okay, so notice that says x is 1, y is 1, and that says x equals 3, y equals 1. Okay, so I can have so that's an ideal solution matrix. That one is ideal, where I have ones on the diagonal, zeros below, and zeros above. That's the ideal one. But I don't need to get the ideal one. That's extra work. All I need to get is a more general solution matrix, which is represented down here. So for a 2 by 2 system, I'd have 1, A, B, 0, 1, C. So the A, B, and C are other numbers. For a 3 by 3, I'd have 1, A, B, C, 0, 1, D, E, 0, 0, 1, F. Again, where the A, B, C, D, E, F are other numbers. And then I go ahead and solve the system by back substitution. So this bottom one right here says Z is equal to F. So Z is equal to this number. Then I can just use back substitution to solve for the Y and the X. Note, ones are on the what we call the main diagonal right here. So that main diagonal is 1, 1, 1, 1, 1. If I had say a 4 by 4, so the next one down, if I had 4 variables, I would actually have a 4 by 5. So I would have 4 columns and 4 rows, 4 columns and 4 rows. Okay. Actually, I'd have 5 columns. So I'd have X, Y, Z, and then another variable, equal sign, column. But we aren't gonna make one that are that big. The whole point of this is you have ones on the main diagonal, zeros below it. Ones on the main diagonal, 0 below it. So this is called a row echelon matrix. So it's called row echelon matrix. Echelon just means they're at an angle. So that the ones are at an angle, the ones are at an angle. A row echelon matrix where the ones are on the main diagonal and zeros are below the diagonal. Okay, going up to the top of the next column. The idea is to go from the system matrix to the augmented matrix to the solution matrix. So 3 steps, bomb, bomb, bomb. How do you do that? Is by using what are called row operations. And there's 3 basic row operations. The first one is I can swap any 2 rows. So I can swap rows around. 2, I can't change elements in the row, not directly, but I can swap 2 rows. The second one is I can multiply any row by a number. That's how we change numbers in the row. So we multiply that row by a number. And the third one is I can add 2 rows to make a new row. And those are exactly the same steps you use to solve a system that has the X's, the Y's, and or the Z's in it. You do those 3 things when you do that. Okay. So the method then, that's how we do it with row operations. So the method is 1, write it in standard form. So write it in standard form. Line up the X's, the Y's, the Z's, the equal signs, and the numbers. Then 2, write the augmented matrix. So what you do is you work vertically. So you put the system matrix on top right here. Underneath it, I put the augmented matrix. Then I do the row operations and I'll get the solution matrix. And then I can solve for the variables by using back substitution. A couple of notes down here on the bottom. 1, write what you do each time. That's an important step. Say what you do. That way you can always go back and check your work real easily if you come out with some sort of bizarro answer or you know it's not correct. Then you can go back and check what you did. 2, get the top left-hand one first. So I want to get the top left one first, and then I get zeros below it, and then I work from left to right. So we're going to start out tonight solving that 3 by 3 that we set up last time. In fact, we'll set it up again so you can see what's going on. So any questions then on the review or any homework before the review? Like any homeworks that you might have done already. Remember, we're going to turn in the homeworks hard copy next week.
Just by looking at some of the examples in the book, the author just doesn't always put that first one first. Is that?
No, that's because the author is taking a sidetrack. Follow my method and it'll be right every time, first time, no muss, no fuss.
All right, because the last one was really weird about how a lot of fractions.
If you do another method, that's okay. But I'm giving you one that you do it this way every time. Because I like, coming from a military background, I like to standardize stuff as much as possible. So I'll do the same routine every time, and then it always comes out right. No muss, no fuss. But I know what you're saying. So with this book, you just got to, take it with a grain of salt and roll with the punches. Any other questions there? Okay, then let's continue with that example that we did last time. Let me see. Just a minute. Let me get over here. And I'm going to turn on this other light momentarily here. Let's see. So we were doing example 2 over on page 540. And I'm going to go ahead and start from 0. Okay, we had just set up the augmented matrix, but I'll go ahead and write the system matrix, the augmented matrix, and I think we had swapped 2 rows, but that's all the further we got on that one. But let's set it up. Let's start it from 0 on this one again. Okay. So anybody want to take any pictures of the boards before I erase them? So this is our second board here. This is our first board over here. Okay, then let me clean up this board. And we will get this show on the road. Anybody have any problems getting the book? Again, you should be able to get it, get a rental or a digital copy via Amazon or Google or something like that. The rental copy is actually the cheapest way to go, I think. Anyway, here, let me turn out. I'm going to keep that light on momentarily, and then I'll turn it out while I put this up. Let's see. So this is example 2 on page 549. So what section are we in? 8.6. Okay. So one, I have 2x minus y plus 4z. 2x minus y plus 4z equals negative 3. Negative 3. Negative 3. Then 2. I have, so 2, I got a missing term. So I got x minus 4z. But notice once again, I'm lining stuff up. I'll just leave a hole there. Is equal to 5. Then 3, we have 6x minus y. Plus 2z equals 10. Okay, so there's my original system, my starting point. I've numbered the equations, lined up on the x's, the y's, the z's, the equal sign, the numbers, put a line under the whole thing. Okay, so from that, I'm going to make the augmented matrix right below it. And I leave some room out here on the left-hand side to say what I'm doing. So here I got 2, 1, 6. And then I got -1, 0. So if there's a hole, I put a 0 in there. -1, and then 4, -4, 2, dash, 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 dash. And then I have -3, 5, and 10. And I close it off with a bracket on this side. So there's my augmented matrix. Now, right away, I want to get this one up here first. That's the tip for starting. And I noticed that I can swap these two right here. So the way I indicate that is just a double-ended arrow right there. I'm going to swap them. That's not a very good one. Hang on. There we go. Zoop, boop, 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 boop. So I did a swap, swapping those two rows. Okay, then I'm going to write it down again before I start doing any operations. So once I get this top, once I get that 1 up there, that row is going to stay the same. So I'm going to have 1, 0, -4, dash, 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 and 5. That's row 1. Okay, so below it, I'll have 2, -1, 4, -3. I also notice I got a 1 there. It's negative, but it's a 1. Hey, that's easy to change. And then the last one, I'll have 6, and then -1, 2, and 10. There we go. Okay, good. Once again, X's, Y's, Z's equals numbers. Okay, good. Looking good. All right. So now what I want to do, now I want to get these two zeros. Notice once I make this a 1, I can multiply it by anything I want and get rid of the number right below it just by using addition. Okay. So that's what I'm going to do. I'm going to go up here. So notice I'm working vertically right there. I'm running out of room right here. So I'm going to go up here. Once again, my top row is the same. So 1, 0, -4, dash, 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 and 5. Bracket. Okay, so I want that to be a 0 there. So what I'm going to do is go -2, and I'm going to say what I'm going to do it right here. I need some more room. So right here, I'm going to go -2 times row 1 plus row 2. So in my symbology, I put the rows with circles around them, just like I do over here. And if I have a number in front of it, then I'm multiplying that row by that. And I'm doing that operation to this matrix right here. So I'm going -2 times +1 is -2 plus 2 is 0. So now I got my 0 right there. -2 times 0 is 0 plus a -1 is -1. Notice we always just do multiplication and addition. That's all we're doing. Now I got -2 times -4 is a +8 plus 4 is 12. -2 times 5 is -10 minus 3, -10 plus a -3 is -13. I'm going to double check this one here. So -2 times -4 is +8 plus 4 is 12. Okay, good. That's good. Now, my next, I can do my operation on this one too. So I want a 0 there also. So I'm going to go, whoops, -6 times row 1 plus row 3. -6 times row 1 plus row 3. So -6 times 1 is -6 plus 6 is 0. And I got a 0 there. Excellent. That's what I want. -6 times 0 is 0 plus a -1 is -1. Okay. -6 times, where am I? -6 times -4 is +24 plus 2 is +26. Finally, -6 times 5 is -30. -30 plus 10 is -20. Okay, don't be alarmed if the numbers get a little large. That's okay. All right. So now I'm looking good. Now I'm going to write down again. Again, the top row is the same. 1, 0, -4, dash, 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 5. Okay. Now on my second row, I want that to be +1. So I'm going to multiply row 2 by -1. So I'm going to go -1 times 2. Okay. And that'll become -1 times 0 is 0. Notice once I get the zeros below the 1, they don't change. They always stay there. So -1 times -1 is +1. -1 times +12 is -12. And -1 times -13 is +13. Okay. Now, I'm going to use this row right here. I just changed the sign in that one. So I'm going to use that row to make this a 0 right here. And notice all I got to do is add row 2 and row 3. So right here, I'm going to go 2 plus 3. So notice right here, 0. So 0, and I'm adding it to these numbers right here. So 0 plus 0 is 0. +1 plus -1 is 0. -12 plus 26 is +14. Is that right? Let me check my arithmetic there. Let's see. That's 6, 2. That looks good. And then finally, I got +13 minus 20 is +13 minus 20 is negative. +13 minus 20 is -7. Okay, good. Now notice I almost got the complete thing. So all I gotta do is one more step here. Now top row stays the same. 1, 0, -4, dash, 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 5. Next row stays the same. 0, 1, -12, 13. In the last row, I want that 14 to be a 1. So I'm going to multiply row 3 by 1/14. So I'm going to go 1/14 times row 3. Okay. Now don't, oops, hang on, I didn't line it up. Wait a minute. Up a little better here. There we go. 1/14 times row 3. So 1/14 times 0 is 0. Again, once I get the zeros, they're going to stay there. 1/14 times 0 is 0. 1/14 times 14 is 1. That's the one I want. And 1/14 times -7 is -1/2. Okay. Now I'm ready to solve it. Notice I got 1s on the main diagonal, 0s below the main diagonal. And this tells me that right here, z equals 1, -1/2. So z is a -1/2. Did we get that right? We get that right. Yeah, z equals -1/2. All right. Okay, then I back substitute into equation 2. So in equation 2, I have y minus 12 times -1/2 is equal to 13. So notice this is going to be a +6 right there. So I got y is equal to 13 minus 6 is equal to 7. So I got y equals 7. Okay, and then I go back into the first equation right here. So I get in the first equation, x is equal to, I'll get a little bit ahead. So that's the equal sign right there. So I'm going to have 5 plus 4 times -1/2. So I go up here. So x is equal to 5 minus 2. So x is equal to 3. So my ordered triple for the solution is 3, 7, and -1/2. Okay, so that's how we do it, just by manipulating the numbers to get the ones on the main diagonal, zeros below it. So we don't have to break it down into some 2x2 system by working with 2 sets of equations, solve that, and then go back and solve for the other equation. Okay, so any questions on how we did that? All right, we're going to look at another one right here. Let's see. Oh, I know what I want to do. I want to do a word problem here. Okay, so I assigned some word problems. Hang on just a minute. Where did I put the word problem? Oh, it's over here. Right. So we're going to do problem 22 from the exercise set at the back of this section. So let me read problem 22. Now, this is your classic coin problem. Okay. Classic problem. They love to ask these on things like placement exams and stuff like that, because they know it's going to mess people up. Okay, so this says problem 22, and it's over on page 551. It says a collection of 43 coins consists of dimes and quarters. The total value is $7.60. How many dimes and how many quarters are there? And people are going, oh man, okay, I'm just going to start counting dimes and quarters, and I don't know what I'm doing. Okay, but if you set this up systematically with a matrix, all right, it'll come right out. Okay, so let's go ahead and do that. All right, so here you got to know the value of money. Okay, but we can set up, first you're going to set up the system. And this is just a 2x2 system. That's why I picked it. So it's 2x2. I wouldn't want to do a 3x3 with coins. It can get a little dicey. Okay, hang on just a minute. Where'd my blue guy go? Okay, still good. How's he doing? Still good. Okay. Dig. All right. Yeah, let me clean up this board right here. Okay. So this is 8.6. Problem 22. Page 551. Okay. So we got dimes and quarters. and we have 43 of them. So right there, that gives me an equation. Okay. That's it. So equation number 1, dimes. I use D for dimes plus Q for quarters is equal to 43. Just like that. Okay. Now the second one is a value mixture. So remember, you're working in dollars or cents. So they give us the total amount in at $7.60. So that's 760 pennies. A dime is 10 pennies. So this one is the easiest way to work. This one is to work in cents. So this would be 10D plus 25Q is equal to 760. There's my system. So each dime is 10 pennies. Each quarter is 25 pennies. And if I count off all those pennies, I'll have 760 of them. So there's my system. So right below that, I'm going to write my augmented matrix. Down here. So I'll have 1, 10, 1, 25, dash, 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 43, and 760 bracket. There we go. So I have a 2x3 matrix. And notice I got a 1 up there already. Excellent. That's what I want. Okay. So then I'm going to write that one down again. 1, 1, dash, 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 43. Okay. All right. So I'm going to say what I'm doing right here. I want -10 times row 1. Let me get some more room right here. Hang on. Yeah. Good. So I got -10 times 1 plus 2. Okay. And that should be a 1 in there. There we go. So negative, my other one right here. And hang on just a minute. Oh, I know, I messed myself up right there. Okay, good. So right here on this row here, to get this row, I go -10 times row 1 plus row 2. Good. Okay. So -10 times 1 is -10 plus 10 is 0. That's exactly what I want. -10 times 1 is -10 plus 25 is +15. -10 times 1 is -10 plus 25 is +15. Okay. -10 times 43 is -430 plus 760. You got some room over here on the side. That's 033 is +330, which I like because 15 is a multiple of 330. So finally I go, I like this one, 1, 1, 43. And I'm going to go 1/15 times row 2. So 1/15 times 0 is 0. Again, once I get those zeros, they don't change. 1/15 times 15 is 1. 1/15 times 330 is 22. I do believe. Is that right? Okay. So right there, I got Q is equal to 22 coins. Okay. Did I get that one right? Is that 22? Or is it 20? What is it? So 330 divided by 15.
22 looks good. Let's go with it.
All right. Okay, I'll buy that. Then dimes is equal to 43 minus 22. So dimes is equal to 21 coins. Okay, so I have 23 quarters and 21 dimes. So look at that. We did that. No muss, no fuss. Just following our matrix solution method right here. Okay. Leave yourself some room over on the side to say what you're doing, and then leave yourself some scratch paper room over on the side too to take care of minor mathematical operations like that. Okay. So any question to solving a system using a matrix, whether it's a 2x2 or a 3x3. Again, get that upper left one first, get the zeros below it, then get the middle one next, get the zero below it, and then get the final row one last, and you've solved the system. Then you just use back substitution to find the rest of the variables. Okay. I like it. Whoops, hang on. Let's see. So I'll give you a coin problem here. Good. Good. I got a coin problem and a value mixture problem, but both of them are 2x2s. I'm pretty sure. Let's see. Yeah, both of them will result in a 2x3 system. They're two variables. Okay, good. Let's see. Oh, the last thing I wanted to do is demonstrate an inconsistent or a dependent system. What happens if you get an inconsistent or a dependent system? And it falls out real quickly on those. So let me go ahead and do those. So this is, and I picked some problems from another section. So these are from section 8.2, because I want to see what it looks like if you get one of those. Okay. Hang on just a minute. Any questions on this one? Okay, good. So let's do over in this column right here. I'm going to do 8.2, number 17. No, let's do an inconsistent first. So I'll do 8.2, number 37, which is an inconsistent system. Now, you don't know it's an inconsistent system. So I'm going to write it down right here. But again, they're 2x2s to keep it simple. So here we have 6s plus 9t equals 12. 6s, 6s plus 9t equals 12. And then number 2 is 4s plus 6t equals 5. 4s plus 6t
Does that say 8.2?
equals 5. Say again? I'm sorry, I didn't hear.
Yes. Yeah, it's 8.2.
Thank you.
Yeah, it's 8.2. So the author didn't have any examples of these in 8.6, but I want you to see what happens. So once again, I'm going to write down the matrix, the augmented matrix: 6, 4, 9, 6, dash, 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 12, 5. Okay. Good. So I want to get that upper left-hand one first. So what I'm going to do is, and let's see. So down here, I'm going to go 1/6 of row 1. So once I do 1/6, 1/6 of 6 is 1. That's good. 1/6 of 9 is 3 halves. So that's 9/6, which is 3/2. Dash, 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 dash. And 1/6 of 12 is 2. Then I got 4, 6, 5. Okay. So now my last one right here, top row stays the same. 1, 3/2, dash, 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 2. It goes like that. So I want to use this one to make that 4 a 0. So I'm going to go right here. -4 times row 1 plus row 2. So -4 times 1 is -4 plus 4 is 0. And I got my 0 right there. Good. -4 times plus 3/2 is -6 plus 6 is 0. Uh-oh. -4 times 2 is -8 plus 3 is -3. So notice what I got here. 0 does not equal -3. So that's a false statement. So that means the x, y is the null set or no solution. Okay, so I got a false statement. You end up with a no solution. But notice it came out in a couple of steps there for a 2x2. It came out false statement. All right, let's do one more. Okay. Now I'm going to erase the whole thing here. So the next one will be a dependent system. But once again, we don't know that. So this is dependent system 8.2, number 17. Okay. So my system, so I have 4x minus 2y equals 6. And for number 2, I have 2x minus y equals 3. Now, this is a fairly simple one. You might be able to see that it's dependent already, because if I just multiply this one by 2, I get that one. Okay, but you don't know that. Okay, especially if fractions are involved, then it could be rather deceptive. So I'm going to make my augmented matrix. So 4, 2, -2, -1, dash, 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 6, 3. Okay. So I want that one to be 1. So I'm going to go 1/4 times row 1. So that'll give me 1, -2, dash, 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 and 4 times that is 3/2. 3/2. Okay. I'll write down the second row right there. Now I want that one to be a 1. So the top row I'm going to leave the same. So I got 1, -2, dash, 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 3/2, boom, boom. Okay, so this one here I want to be 1. So I'm saying what I'm doing over here. So I'm going to go -2 times row 1 plus row 2. So -2 times 1 is -2 plus 2 is 0. -2 times -1 is +2 plus a -2 is 0. Uh-oh. Let's see. -2 times +3/2 is -3 plus 3 is 0. Oh, man. Okay, but that's okay. So here I got a true statement. A true statement. So the way we say the solution is, let me write it not in green because that's hard to see. We got the set of all x, y such that, and then I just write down one of my original equations, 2x minus y equals 3. And there's my solution in set builder notation. That means anything that satisfies this equation satisfies the system. Okay. So you can see if you get it for a 2x2 in at least two, maybe 3 steps at the most, it'll fall out and you'll see that it's either a dependent or an inconsistent system. Okay. So any questions on those?
Yeah, Professor. When you did the 1/4 times row 1,
Uh-huh.
how did you get -2 still?
Okay, let's see. Right here. So I got 1/4 times 4 is 1. 1/4 times -2, the 2's divide out and I get -2. Oh, my bad. It should be what?
On my calculator, I got -1/2.
Oh, it should be -1/2. Okay.
Okay.
Thank you very much. So this should be -1/2 right here.
Okay, that's all.
Okay. Is the last one correct? 1/4 times 6 is 3/2. Yeah. And then down here, so that'll be 1/2. So then I get -2 times -1/2 is +1 minus 1 is 0. Okay, good.
Cool.
You can see I just tucked myself into a slight mathematical error. Anyway, which you can see how easy it is to do, especially when you do that, you're doing multiplication and addition at the same time. So with simple numbers like we've been doing, it's not too bad. So with more complex numbers, like say in a value mixture problem, then it could be a little more difficult. Now we're going to look at more difficult value and interest mixture problems in the next section, where we're going to look at a different method to apply. Okay. In this next method, I call just like the quadratic equation is the super duper power tool for solving quadratic equations. You can do it, write down the A, the B, and the C. You just plug and chug. It'll give you the solution or no solution every time. So what we're going to look at next is I call the super duper power tool for system solving, which is going to be something that we call Cramer's rule. Cramer's rule. Okay. And it's fun. All right. Just like this is fun. Don't you think it's fun working with the numbers like that? No letters. Oh, maybe not. Okay. That's okay. All right. Stand by. Let me turn on this light here so I can see a little better. So now we're going over to 8.7 and we're talking about, let me get to 8.7 here in my book. 8.7. Yeah, that's 8.8. Didn't want to go that far. Ah, 8.7. So it's called determinants and Cramer's rule. So here we're going to solve a system with determinants. And the method for doing that is something called Cramer's rule. So we'll put all of that together and you'll see that it's a nice handy way. Even we're not going to do the 3x3 because that takes a little bit more effort and it's a little bit more time consuming. So as long as you know the basic procedural method for a 2x2 for Cramer's rule, then you're good to go. And then just with a couple of extra additional bits of information, you could apply it to a 3x3, but we're not going to do that. All right, so let me go over here. And go back over one. All right. So we're going to solve a system with determinants. Okay. So we need a little definitions right here. Okay. So it says determinants and Kramer's rule. So we're actually solving a system with determinants. The method that we use is called Kramer's rule, and we'll go through that separately. But first we need to know what a determinant is. So a determinant is a real number value for a square matrix. Okay, so a couple of key things right here. It has to be a square matrix. So that's like a 2x2, a 3x3, a 4x4, etc. So it's a square matrix. Okay. All right. And so let me give you the rule to follow. So I have my general square matrix, A, B, C, D. Okay, so that's my square matrix. Now, to make it, in fact, let me back it up. I need a little more room because I only have half as much board as I normally have. Let me back it up a little bit here. Over to here. A, B, C, D. So it's 2 rows, 2 columns. Then this is the matrix. This is the determinant. Now, let me back up a little bit. More room. Okay, so it's a number value for a square matrix. So we start with a square matrix. I make a determinant by taking away the brackets and putting straight lines on either side, and then I can write the values. Okay. Okay. All right. Now we need a rule to follow. Okay. So this is the method. The method to get the value. All right, go down here for a minute, and I'll stand up here in a second as soon as I write it up here. So, okay, so we got, yes, start and end. Okay, good. In fact, I don't have enough room down here, so I'm going to go up there. There. Okay. Okay, so there I have the determinant written right there in blue. So I start here in the bottom right-hand corner, and I multiply diagonally up to the upper left-hand corner. So D times A is AD. And then I swing around this way. Minus B times C equals minus BC. So I get AD minus BC. So start in the lower right-hand corner, multiply up to the left, swing around, it's minus, and then lower left to the upper right. Okay, we'll do some examples and it'll all work out. Once you do it a couple of times, you'll pick up the pattern, and it's no big deal. You go, oh yeah. Where it is a big deal is with a 3x3, because there's other things that we got to do with a 3x3. And we aren't going to do that because we just don't have enough time. Okay, so let me give you example 1 here. Make sure I got the right example. 2, 6 minus 5, 7. Is that right? 2, 6 minus 5, 7. Okay. So example 1. So we're going to evaluate this determinant. 2, 6 minus 5, 7. Okay. So again, I'm starting here and I'm going this way, swinging around this way, and going back this way right here. So it's going to be 7. Hang on, let me put an equal sign in there. You can see sign errors are very prevalent in doing this. So I got 7. Dang it, I want to put an equal sign in there. Equals 7 times 2 minus 6 times negative 5. So then I got 14 plus 30. And the final value is, put some room in here. 14 plus 30. Final value is 44. So this only applies to square matrices, and it's a number value for that square matrix. Note. Only for square matrices. Okay, so that means the rows equal columns. That makes a square matrix. Okay, so 2 by 2, 3 by 3, 4 by 4, etc. Once you get up to the up above 3 by 3, it's far too difficult to do by hand. The 3 by 3 is doable by hand, but it takes extra work and it's more time consuming.
Why,
So
can I ask a question? Why is it a -6? Like -6 times,
no, it's minus 6 times -5. There's
Where-
the minuses the minuses between when you swing around this way, there's a minus sign in there. See the
Got it.
general rule up there? When I swing around that way, there's a minus sign there.
okay, perfect. Thank you.
Okay. So it's minus a positive 6 times a -5.
Got it. Thank you.
Okay. So you really have to be careful of your signs. But once you see the Kramer's rule, this is literally a plug and chug method. There's no number manipulation. You don't worry about variables or anything like that. It's plugging and chugging, just like that. That's why I call it the power super duper power tool for system solving. Just like the quadratic equation is just plugging and chugging. All I do is plug the numbers in and I chug this. I chug the value out. All right, so that's what we're doing here too. Okay, so let me see. Hang on. What's next? Let me go over here, see where we are. Okay, now we're going to look at the Kramer's rule. Okay, and the KISS principle applies to Kramer's rule. It's going to look a little bit detailed and intricate, but it's not really. Yes, Dakota, what's your question?
I was gonna say somebody in the chat asked what the R equals C was, but then somebody else typed in rows and columns. So
Oh, yeah, rows equals columns. That's correct. Thank you. Yeah, I should go back periodically and check the chat. But yeah, keep an eye on it. If someone asks a question, let me know. That's good. And I'm glad somebody else answered it. Perfect. All right. So what are we going to do? Oh, yeah. So now we're going to do the Kramer's rule. Okay. So Kramer was this mathematician that saw the patterns in this and was actually able to develop this rule that applied the patterns. And so it would come out every single time he did it. Amazing. All right. Okay. You're going to like it a lot. Let's go over to the other side. Oh, I tell you what, let's take 10. And when we come back, we'll lay out Kramer's rule right there. Okay. So take 10. So let's see. I'm not going to stop the clock, but now it's 8:16. So the math train leaves the station at 8:26. All right. And I get some more water here. So I'm going to turn off my microphone while I go take care of an errand here, and then I will be back. And I can Okay, there. Back on there. Let me open up the chat here so I can see anything, questions have come up. Oh, no, I don't want to do that. There we go. Let's see. Okay, good. Any other questions while we're just hanging here for the next couple of minutes? Puppies, puppies. What? Sad puppy faces. She knows I have a cookie or something, so she's out here zeroing in on it. Let's see. What are we going to get to next there? Oh, yeah, Kramer's rule. Okay, okay. The dog. Okay, good. We'll get started again. So the author goes over a little bit of development of Kramer's rule. I'm not going to develop it. I'm just going to give you the rule. And well, he's got the rule actually at the top of page 554. So he doesn't go into developing. Some books do. But I'm just going to give you the rule. But first, I'll let you see the pattern that that Kramer came up with. right. Let me go back over to the other side. Now, let's do this. Clean up this side here. Okay. Okay, so for Kramer's rule, we're just going to start off with a very basic system. Okay, so it's going to look like this. The first equation is a sub 1 x plus b sub 1 y equals c sub 1. I'm just going to use a, b, and c. The subtext 1, the subscript 1, 1, 1 indicates that it's from equation 1. Okay. In equation 2, a sub 2. No, what are you doing? You can't be up there. Look. Here, she just got up on my seat. Get down from there. No, you can't be up there. She knows there's something good to eat up here. A sub 2x plus b sub 2y equals c sub 2. There's my system. 2 equations and 2 variables. Okay, so we set it up with determinants. And in some books, you might see this. X is equal to d sub x over d, which is the x determinant over the coefficient determinant. Okay, the x determinant over the coefficient determinant. Likewise, y would be d sub y over d. Okay, same thing, y determinant over the coefficient determinant. Now, the thing when we solve this, you only do it as many times as you need to do it, especially for a 3 by 3. If I only have to do it to solve for 2 variables by determinant, that's what I'll do, and I'll solve for the 3rd variable with substitution from one of the system equations. Okay, so let me write down then what the x determinant is, and I'll write down what the y determinant is too. So the x is going to be a determinant on top divided by a determinant on the bottom. So on top, what we do is we take the c's right here and we put them into the x column. So I'll have C1, C2, and then B1, B2. And over here, I take the just the coefficient determinants here. A sub 1, A sub 2, B sub 1, B sub 2. Okay. Then for y, that's equal to a quotient of determinants also. Now the denominator determinant is the same. A sub 1, A sub 2, B sub 1, B sub 2. So once you define the coefficient determinant, it's the same for all of the variables. If I had a 3 by 3, it would be the same for the z also. And then up on top here, I take the c's and I put them into the y column. So I'll have A sub 1, A sub 2, C sub 1, C sub 2. So once again, it all hinges around just all the numbers again. All we're working with numbers. So for the x's. So first off, the denominator is the coefficient determinant. It's the determinant of these four numbers, A1, A2, B1, B2. A1, A2, B1, B2. Okay. The numerator for the X, I take the C's and I put them into the X column. So C1, C2, B1, B2. For the Y's, I take the C's and I put them into the Y column. A1, A2, C1, C2. And that, ladies and gentlemen, boys and girls, is Kramer's rule. Right there. Okay. For this system right here. Okay, so let's look at an example. All right. Let's see. Let's do example. Looks like we just got one 2x2 example, but I think I'm going to do a word problem here too. Yeah, so let's do example 2. 2, 5, 5, 2. 2, 5, 5, -2, 7, -3. Okay, good. So let's do example 2. We'll do it over here on the side. So you can see we are actually, so I titled this over here, solve with determinants. And that's what we're doing. So I am in fact solving it with a quotient of two determinants. That quotient is determined by something called Kramer's rule. So that's the methodology that we're using. But the tool that we're using is the determinant. Boom, the determinant are the nuts and bolts of Kramer's rule. So let me write my system over here. So notice, I don't have to write the augmented matrix. All I need to do is plug it right in and chug the solution out. So here we got wait a minute. Where was it? Oh, 2x plus 5y equals 7. And for 2, I have 5x minus 2y equals -3. There's my system, okay? So x then is going to be a quotient with a determinant on top. Let me get some more room right there. Hang on just a minute. Some more room. Where's that 2 right there? Okay. There we go. We're going to determine it on top. So on top, I'm going to take the 7 and -3, put them over here. So I'll have 7, -3, and 5, -2. You can see where you have to be very careful of signs. In the denominator, I'm going to have 2, 5, 5, -2. And that's going to be equal to. Now I'm going to write out all of the numbers. Write the numbers down. Don't try and do the multiplication and addition in your head as you go. Write down what everything is. So here I'm going to have -2 times 7 minus a -3 times 5. So -2 times 7 minus a -3 times 5, because there's a minus in between right here. On the denominator, I'll have -2 times 2 minus 5 times 5. Okay. So x then is equal to, on top, I'll have -14 plus 15. And on the bottom, I'll have -4 minus 25. So this is equal to -1 over -29. So x is equal to -129. Okay. So notice if I did that with my traditional methods, that's going to run into a lot of arithmetic. And here it's just plugging and chugging. Now I already have the denominator. So I could go back here, or I could just say y is equal to, all I need is the numerator determinant. So I take the 7 and the 3, I'm going to put it in there. So I'll have 2, 5, 7, -3 all over -29, because I already figured out that number, okay? So then this is going to be equal to -3 times 2 minus 5 times 7 all over -29. So y is equal to, hang on, let me get down here. Yep. So I got -6 minus 35 all over -29. Now notice a negative divided by a negative is a positive. So 6 plus 35 is 41. 41 over 29. So notice the answer that I got. So my XY solution, I'll write it over here so you can see it. So I got XY is equal to -1/29 and 41 over 29. Okay. So you can see if I had to solve that by other methods, you know, it's going to take a lot more arithmetic and be susceptible to a lot more sign errors. Whereas here I'm just plugging and chugging. Okay, isn't that fun? Here,
Quick question, Professor.
yes, go ahead.
So when the -14 plus 15,
Uh-huh.
that's supposed to be minus, or how did you get the plus 15 for the X?
Well, oh, right here.
Yeah.
So it's -2 times +7, -2 times +7, swinging around, minus, -3 times +15, -3 times +15. So that gives me a -14 minus times a minus is a positive plus 15. Okay,
Okay. It's still a little confusing, but yeah, I get it.
I know. Yeah, you got to be careful of your signs. Okay, hang on. I think I got another one here waiting in the wings. Because the author only did one example in the book. Okay, good. So I'm going to do also 8.3 example 5, because it has decimals in it. Okay, so 8.3 example 5 was the fertilizer mixture problem. And here we're just going to crank out the solution, bang, 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 just like that. In fact, let's read 8.3 example 5 just to let you know what it says. So let me go back to 8.3. So notice I don't even have to write down the augmented matrix here. 8.3, example 5 on, what the heck is it? Oh, the top of page 523. Okay, hang on. Let me put this over there. So 8.3 example 5 says, Nature's Green Gardening Incorporated carries 2 brands of fertilizer containing nitrogen and water. Gentle Grow is 3% nitrogen, and Sunsaver is 8% nitrogen. Nature's Green needs to combine the 2 types of solution into 90 liters of mixture that is 6% nitrogen. How much of each brand is used? So once again, we could use a table to get our system. So that's where the table comes in. So we're still not knocking out the table. We're still using that because we need to get the system. And then we got to solve the system. Okay. So let me write the system that we get right here. Okay, good. Hang on. I need to get more board space. Okay, Wait a minute. Where'd it go? Yeah, here we go. Okay. Okay. So this is a percent mixture problem. So in the first place here, we're going to use a table to get the system. This is the system that we get. So we get G plus S equals 90. And 2. I got 0.03 G plus 0.08 S, I believe, is equal to 5.4. Okay, so there's my system. Put this over here.
Oh, where'd you get the 5.4 from?
The 5.4 is 90 times 0.06.
Gotcha.
We get that out of the table. Okay, we set this one up in the notes for 8.3. I think we did. Anyway, that's what we get. So 5.4 is 90 times 0.06. So the mixture is 6%. So 6% times 90 is 0.06. That's where you get that. Okay, so let me set it up then. So for green, G is going to be on top right here. I take the 90 and the 5.4 goes right there. We get some more room right here. Hang on. Got cramped. Okay. Got 90, 5.4, and then I have 1 and 0.08 all over 1 and 0.03 and 1 and 0.08. Okay, and I'm not even getting rid of the decimals. I'm keeping the decimals in there. Okay, so 0.8 times 90, 0.08 times 90 is 7.2. So I'll have, I'll put everything in here. So I go 0.08 times 90 minus 5.4 times 1. All over 0.08 times 1 minus 0.03 times 1. Okay, so G then is going to be on top. I get 7.2 minus 5.4 all over 0.8 minus 0.3. Excuse me, not 0.8. It's 0.08 minus 0.03. So we end up, the difference between those two is going to be, I think 1.8. So I think between 12, 6, 1, 7. Yeah, so I got 1.8 all over 0.05. So again, I'll use my calculator for that to crunch that out. Let's see what we get. So I get 1.8 divided by 0.05 equals, and I get 36, and it's liters. So 36 liters, okay? Notice, no muss, no fuss, I'm just crunching it out. To get the S, so S is going to be, the denominator is 0.05, and the numerator is going to be 1.03 and 95.4. Okay, so going over here, I'll have 5.4 minus 2.7 all over 0.05. So S is equal to, the difference between that and that is what? 2.7. So 2.7 divided by 0.05. So S is equal to, clear, 2.7. Hang on, clear. 2.7 divided by 0.05 equals 54. Right there and right there. Notice 54 plus 36 is 90. So there's a quick check. So notice once again, the beauty of this method. So it crunches right out. Okay, so again, the hardest part is getting the system equations. Just like I said, and originally setting these up for multivariable word problems, the hardest part is getting the system equations. Solving is usually it can be the easiest part, especially if you use a system like this. So we didn't get rid of any decimals. We just put everything in, all of the decimals, all of the numbers, and just cranked it right out. Okay, isn't that nice? You like that? Come on, I know you like it. Okay, you can admit it. All right, let's see. And again, we're going to skip the 3 by 3. So let me go back to that section. Hang on. So 8.7. So we're skipping objective C, the 3 by 3, solving a 3 by 3 system. Objective C and D. So C is determinant for a 3 by 3 system. And then D is Kramer's rule for 3 by 3 system. Okay. Again, you can look in the book and see what it is. You can try out a couple of problems if you want. I'm not going to assign any for homework, and I won't test you on any. I will test you on Kramer's rule for a 2 by 2 though. So I'll expect you to solve both of the equations. So the beauty is once I get the denominator right here, once I get the denominator number, it's the same for both of them. And that's what it was in the other one too, is that negative 29, where we got those really bizarro fractions, but it was the same for both of them. Okay. Excellent. So then we will move on to 8.8, where we're going to talk about some business and economic applications. So just a couple of simple applications here for a business rule and then for an economics rule. Okay, but really simple. So for the business one, we're going to talk about what's called the break-even point, and we'll talk about what that is. And for the economics rule, we're going to talk about the equilibrium point. So the break-even point and the equilibrium point, and we're going to kiss it. We're just going to keep it simple, 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 simple. Okay, hang on just a minute. I need to get a drink. Okay, good. Go back over to the other side. Okay. So any quick questions, once again, on calculating a determinant? Remember, it's just a number value for a square matrix. And we're only looking at the 2x2s. We're not going to the 3x3s. But you can do it for a 3x3 too. 3x3 also. It just takes a little bit of extra work. All right. I like to do the 3x3. It's fun, but we just don't have enough time to do it. Okay. We're already behind schedule. Believe it or not. The online classes always go slower than the classroom classes. Okay, there we go. Mainly because I got to spend a lot of time erasing the boards. In the classroom, I got much more board space, so I don't have to do as much erasing. Okay, so now we're over in section 8.8 on page 558. 8.8 on 558, where we're talking about business and economic apps. We can go. Here we go. Okay. Okay. Applications, apps for applications. Okay, so I'll give you everything in a nutshell. So the two objectives over here are objective A, talking about the break-even analysis, and objective B, supply and demand. Okay. So okay. So our two objectives. Objective A. In the business app, we're talking about profit, revenue, and cost. And the result is going to be something that we call the break-even point. It's made up of that profit, revenue, and cost. Hang on just a minute. I'm running out of ink. Okay. And then objective B, we're talking about supply and demand. This is just to give you the idea of what we're talking about in a nutshell. And over here, we're talking about something which is called the, hang on. I can't remember. Oh, the equilibrium point, my bad. Equilibrium point. So those are the two objectives out of these two sections right here, for business and economic applications to determine what's called the break-even point. And then the second one is the equilibrium point. Okay, so let's do the business app first. The business application. Okay. So, and then once again, we're gonna keep the KISS principle applies. Okay. Okay, so the business applications, there's no special formulas. We're just talking about basic common sense concepts. So in a business, you're setting up a small business, you're making something, you're selling it in some store or maybe your own store. And basically, ultimately, you want to make a profit so you can make some money. Okay. So the profit is equal to the revenue minus the cost. So these are the relationships. The profit equals the revenue minus the cost. Okay. So the revenue is how much money you make for selling stuff, and the cost is how much it costs you to make a particular item. So in here on all of these well, let me say it. Oh, hang on just 1 second. Let me back one up one. Okay. I'm going to put that up there again. Hang on. But I just wanted to write something else first that I forgot about. So our business relationship here is our business makes X items. Okay. And I don't know what it might be. You know, you might be making refrigerator magnets or pencils or pens or scarves or purses or shoes or hats or something of that nature. You're making something that you can make. Maybe you're making birdhouses to sell in the neighborhood. I don't know, but it's X items. Okay. So the different relationships that then make up those X items, we have the profit. And that's equal to the revenue minus the cost. Okay. So how much it costs you to make the things, or excuse me, how much you sell the things for minus how much it costs you to make the things. And notice all of these can be functions. So this is P as a function of X is equal to R as a function of X minus C as a function of X. And again, our functions are going to be very, very simple and straightforward. Okay. But the bottom line here is to make a profit. Okay. Now, the cost has, first let's talk of revenue. So revenue is your amount of sales. Okay, and that's our function, R as a function of X. So how much we're selling stuff for. We also have cost. And cost, you're going to have a bunch of different ways to figure cost, but we're going to keep it simple. Basically, it's fixed cost times variable cost. And this is going to be C as a function of X. Fixed costs are things like all of your overhead, electricity, water, things like that. Where typically variable costs are like parts and labor. Parts and labor. Okay. And all of these things, we're not going to get down into the weeds on determining fixed and variable costs. I'm just going to give it to you. All we need to know is how to determine how to get a profit. Okay, so what we want to do is find what we call the right here, the break-even point. Okay, so that's our whole objectives here.
What does it say next to overhead?
Say again. I'm sorry,
What
I
does-
didn't.
What
I
does it
didn't-
say next to overhead?
Where's what? Oh, overhead costs. This is overhead costs and parts and labor. So typically your fixed costs are your overhead costs, rent, electricity, water, things like that, taxes. Whereas your variable costs are like typically parts and labor. Okay, and that's the cost. That's you combine the two, and that's going to have and you just average it all out, and that's going to tell you how much it costs to make one item. Okay, so the break-even point. Let's talk about that. So we're going to put all this together to find break-even point. So the break-even point is where you start to make a profit. So when you start off your business, you usually operate at a loss, okay? Because you're losing money because you're just not making the stuff. You're not making enough stuff, or people don't know about it. So you got to get some advertising in there, stuff like that. Again, that would probably be part of the variable cost advertising, for example. But the break-even point is where the revenue R of X is equal to the cost C of X, and the net profit P of X is 0. So that's exactly where the business is breaking even. Okay. Let me go over to the other side and we'll expand on that and look at an example. All right. I'll give you a graphical example. In fact, I'll give you the graphic example over here. Hang on. So we call the break-even point the BEP, the break-even point. The BEP, the break-even point. So graphically, what that's going to look like is this. Notice on my graph, everything operates in the number one quadrant. I don't want any negatives right here. But typically, along this side, I got dollars. Okay. And this would be where I would graph, for example, revenue and cost. And down along this side, I got X items. So the number of things that I'm making, okay? Yeah, here we go. So typically we start off with a cost function. So my cost function goes like this. This is C as a function of X. So it's going to start here at some fixed point. But then typically, as I make more items, it costs me more, right? Okay, now I want to go out and sell stuff. So my revenue function typically is going to start where? It's going to start down here, probably at 0, but then it's going to go up like this. And at some point, it's going to be like that. So this is revenue as a function of X. So right here, where the two curves cross, they're two straight line curves, and where they cross is the break-even point. And at that point, R of X is equal to C of X. So the revenue exactly equals the cost. So down here, I'm operating at a loss. So I'm a loss down here. LOSS. But up here, I'm making a money. Profit. Okay, so that just gives you a visual picture of what we're talking about. Again, we're just keeping it real simple. All right, let's look at an example. Okay, good, we're doing good. And so let's see, what do we got in here? Hang on. Example 1. Let's see what it says. So now we're over on the top of page 559. Okay, so example 1 says we're manufacturing chairs. We got a chair business. Hang on, I moved my laptop there. Okay, so it says Renewable Designs is planning to make a new chair. The fixed cost will be $90,000. Okay, and what makes up that $90,000? You don't care. You just want to know that's the fixed cost. And it will cost $150 to produce each chair. And we're going to sell the chairs for $400 each. Okay, good. So let's note what we got right here. So this is example 1, our chair business. Let me go over to the next page. The next board over here. Anybody want any pictures of that board there? A lot of information up there, especially right here off the bat. So off the bat gives you sort of a feel for what we're going to be talking about. Okay. Then over here is the KISS principle of breaking it all down and a little graphical representation right there where we can see the loss, the profit, the break-even point, where the revenue is equal to the cost. Okay, good. All right. Here. Once again, we're just going to keep this real simple. Okay, so this is what section are we in? 8.8, example 1. 8.8, example 1. Our chair business. Okay, good. All right. So let's write down what we know. So I know that looking back in the problem once again. So they told me the fixed cost will be 90K and it'll cost me $150 to make a chair. So right there, I got my cost function. Can you see the cost function? So the cost is equal to fixed plus variable. That's, hang on. Okay, the variable is $150 per chair. So right here, I got C as a function of X is equal to 90,000 plus 150 times X. $150 times every chair that I make. So if I made 100 chairs, that would be $15,000. So 90,000 plus $15,000 would be my total cost. Okay, so they gave me that. All right, what else do we got here? And then we have the, I'm going to sell the chairs for $400 each. All right, so that's my revenue. Notice revenue is just a very basic function. Okay. Now notice over here, this is the Y over here. This is always the vertical axis. This is the X. That's the horizontal axis. So what do they ask us here? I got everything I need. So it says, find the total cost of producing X chairs. Yeah, we found it. Okay. Find the total revenue from the sales of X chairs. Yeah, I put it up there. Find the profit function from the production and sale of X chairs. Okay, cool. Let's find the profit function. So remember, P of X is equal to the revenue minus the cost. So P of X is equal to 400X minus 90K minus 150X. I got 90,000 in there, right? So P of X then is equal to 400 minus 150 is what? 250. 250X minus 90,000. Okay. So I have the cost function right here. The revenue function right here. And the profit function right here. The only math involved was right here in calculating the profit function, but you saw how it was all straightforward. So we're keeping everything as simple as possible. Okay. Now it says, we found the profit function. So it says, what will be the profit for your company to realize from the production and sale of 300 chairs, 800 chairs? So then I'm just plugging and chugging for that. We're not even bothered for that right now. Graph the total cost, total revenue, and total profit function using the set of axes. Okay. Determine the break-even point. That's the bottom line. We want to know the break-even point. With these numbers right here, how many chairs am I going to have to sell in order to start making a profit? Okay, that's where the rubber meets the road. We'll do a very simple graph also just to show you what it looks like. But what do we want to know? I want to know the break-even point. Okay, good. So BEP. Remember, at the BEP, R of X equals C of X. Simple. So my revenue function is, where'd it go? 400X is equal to 90,000 plus 150X. So notice, I just have one variable and one unknown. I can solve for X. Hot dog. Let's continue it up here. You're doing good. Find the break-even point. So let me put it back up here. So I got 400X is equal to 90,000 plus 150X. So then I got 400X minus 150X is equal to 90,000. So that gives me, what was that? 250X equals 90,000 So X then is equal to 90,000 divided by 250, okay? So let's do a quick calculation right there. Notice that's gonna come out to be a nice whole number. All right, I know. So I got 90123, 90K divided by 250 equals, and I get 360. X equals 360 chairs. So that's how many chairs I'm going to have to make in order to start making a profit. Okay. I'm not only have to make them, but I have to sell them. So I got to make and sell that many chairs for me to start making a profit. Now, how would we graph this? They wanted you to graph it. I'll just show you really simply right here. Okay, good. So remember, your graph is going to be in the number one quadrant, plus, plus. We're not worried about any negatives. Okay. So I got dollars and cents over here. And then I got a chairs going this way. Okay. And we're going to call this dollars times 1,000. Okay, just to keep it simple. So notice then I'm going to have, let's see, how am I going to set this up? So let's go like this. So chairs, I got to go out to 350. Okay. So chairs, I'll do by hundreds, 100, 200, 300, 400. So 100, 200, 300, 400. Okay, there's my chair axis right there. Okay. And then this axis right here, let's see, I got to stop at 90,000 there, but then I'm going to start making some money after that. So let's see, maybe I'll go by, I'll go by 50s. Okay, so this will be 50,000, 100,000, 150,000, 200,000, 50, 100, 150, 200. Okay, so I know that it starts at the y-axis intercept. Look at what we're graphing is we're going to graph the cost function first. So there's the cost function. So notice it's in slope intercept form. So here the y-axis intercept is 90. So it's going to be right here. So there's where it's going to start. And then the slope is going to be 150 over 1. Okay. So that means if I multiply the top and the bottom by 2, I'll have 250 over, hang on just a minute. So I'm going to raise, so I'm going to go out 100. Okay, so I'll go out here. So up here on this one right here, hang on. V is equal to 90K. I got that in there. M is equal to 150 over 1. Right? Okay. So what does that mean? So that means I go out, how am I going to do that? No, I can multiply the top and the bottom by 100. So if I go out 100, I'll go up this way, 15,000. Okay, that's good. I can look at that way. So if I go out 1 unit this way, I'll go up this way, 15,000. So what if I go out 3 and 3? So that'd be, so if I did 300 to 3, then I'd go up that way 300 times 150 is 75,000. Okay, that's easier to see. So then I'd have, that's 90,000. So that's 50,000. That's 50,000. So 75,000 would be that much right there. So I'd go up, boom, boom, right there. Okay. So that is my cost function. Okay, now see what I did there? I got this, I multiplied it by 300 over 300. So when I did that, I got 300 on the bottom and 300 times 150. And you can just figure it out this way. 300 times 150 is 45,000. Okay, so that's 45,000. So here, each one of these are 50,000 apart right here. So basically I went 50,000 up to there, and maybe it's a little bit too steep, I think. Yeah. So that would be 50,000 up. So it'd be a little bit down a little bit further. My bad. Hang on. Let me erase that one more time. I went too far. Okay, so if I go 300, that would be 50,000 right there. So it's a little bit below that, maybe about right there. Okay. So there's my cost function right there. So that's C as a function of X. And again, I'm just using my slope intercept knowledge for graphing a straight line. Now, let's look at the revenue function. So that's what goes on the other one. So revenue was, where's revenue? Revenue is 400X. So that means I start here at 0, 0. Okay. Now, if I multiply that by 3, so my slope is 400 over 1. So if I multiply that by 300 over 300, I'll have 120,000 over, I'm pretty sure. Let's see, hang on. Clear. 400 times, let's do 400 times 400 equals, yeah, 160,000. So 160,000. Okay, so 400 times 400 is 160,000, or about right there. So there's my revenue function. And where they cross is the break-even point. Right here is the break-even point. The VEP. And what did I say it was? We calculated it, 360 chairs. Oh, that's not bad. Pretty close, huh? So 360. Okay, 360 chairs. So that's how you would take care of it graphically. So everything down here, I'm at a loss. That's my loss area right there. And everything on this side up here is profit. Now, if you take a course in economics, it's not all that simple, but that's the basics where the rubber meets the road. And looks like we're almost out of time. What time is it? What time we got? 27. We only got 3 minutes left. So we'll look at the next part, the supply and demand next time. So basically, test 1 will go up to this point right here in 8.7, or blame my last 8.8. Okay. Any questions?
Where did that cost function come from?
Right here. So the cost function is the fixed cost plus the variable cost right there. The variable cost is how much it costs to make each chair. So it said $150 per chair. So it's
And how'd you-
90,000 plus 150 times X.
And how'd you get that on the graph there? What'd you say? You took 150 over
Okay.
1 and
So this is in slope intercept form. There's the slope, there's the y-axis intercept. So the y-axis intercept is at 90. So I did that. On my vertical axis here, it's times 1,000. So it's 50,000, 100,000, 150,000, 200,000. So I just eyeballed it in there at about where I thought 90 was. And then what I did was I multiplied it by 300 over 300. So when I did that, I got 300 on there and 45,000 on there. So I went out to the 300 from here, 1, 2, 3, and I went up about what I thought was 45,000. Again, we're just eyeballing it in here. It's a very rough graph. But you can even see with my rough graph, hey, I got a break-even point that looks like it's pretty close to what I calculated. Does that answer your question on that one?
no, I don't see
You
where
have to be comfortable with graphing a straight line.
I just don't see where the 45,000 is on the graph. And 450,000 somewhere?
No. Look, each one of these lines is 50,000 apart. So 45,000 is almost one line separation. So I went out here, 1, 2, 300 and up, not quite to there, but I lowered it a little bit. So right about there. So again, I'm just eyeballing it in there. Just estimating it. Okay, does that make more sense? So again, my graph isn't really accurate. Okay, I mean, my graph paper you see is kind of rough, but I've labeled everything so you can see what all of the values are. So anytime you have a slope, this is the slope. So when you graph a line with slope, you always put it over, you make a fraction out of it. So that's 150 over 1. So the numerator is how far it goes up and down, and the denominator is how far it goes out horizontally. Okay, so if I just have it over 1, obviously 1 is hard to graph on there. So I multiplied it by 300 over 300, and I got an equivalent slope with a denominator of 300 units. I could have done 400 too and gone all the way out there like I did with the revenue.
Okay.
Okay, that's your question. Anybody else got? That's all we got, folks. So make sure you sign into the chat right there. Thank you very much. I forgot to turn off the chat, so I was getting, well, it's not too bad. All right, good. All right, good. Okay, well, I'm going to stop the recording